Hello everyone, thank you for coming to my flash talk. I am Florian Cougoulic and I would like to discuss a project made in collaboration with Yuri Kovshegov about writing an Helicity-dependent extension of the MV model. Since the measurement from the electron-muon collaboration of the J1 structure function, we are lacking an understanding of the proton spin in terms of QCD degrees of freedom. Consider the Rafe-Manohar decomposition of this proton spin. I will focus on the quark spin contribution sigma q. This contribution is given as an integral of a Birkenes of the Helicity PDF, where the helicity is either aligned or anti-aligned with the proton spin. This integral runs from 0 to 1. However, experiment can only access a finite range in X. In the region of small x, there is an opportunity for some unaccounted speed. This motivates the use of small x framework to explore this possibility. In the usual unpolarized case, one can use the G-Mork evolution to estimate the small x behavior of operators. For Helicity-dependent operators, one should use the Helicity G-Mork equation written by Yuri and I to estimate their small x behavior. In a similar fashion to the G-Mork case, an initial condition is needed. This is the purpose of this project to extend the MV model for Helicity-dependent operators. Before quoting our results, I would like to give you some insight of the main assumption and building blocks of our results. The assumption follows the MV model. We require a large nucleus made of many uncorrelated nucleons. Each nucleon is a dilute system of partons. In order to work in PQCD, we require the transverse size probe to satisfy the following ordering. The main building block of our calculation is a correlation function of two source operators. Here, lowercase j denotes the source operator for gluon field, acting only on parton of the state with definite helicity sigma. In a similar fashion, capital J denotes the source operator for quark field. The novel feature is that those source operators depend on the helicity orientation of the partons they act on, and the two-point functions are diagonal in this space. With the assumption that each nucleon is dilute and uncorrelated to other nucleons, one can easily show that any odd combination of source operator vanishes when performing the state average, and any even combination of source operator factorized in product of two-point average. This is a result expected from a Gaussian distribution. Those Gaussian distributions are characterized by the charge densities mu plus, mu minus, where plus minus indicates color charge density from parton with positive or negative helicity. For the quark field, we have another distribution denoted by nu here, which is similar to the charge distribution mu up to some color prefactors. Our main result is the following distribution, which we wrote in terms of field. The Gaussian distribution of source after using the equation of motion takes the following form. Alpha is the usual econal gluon field, beta is the third component of the chromomagnetic F12, and psi and psi bar are the quark and anti-quark fields. We check that this distribution maps back to the usual MV model distribution if one integrates out all the fields which are Helicity dependent. As a prospect to this project, a stochastic formulation of the Helicity G-Mork equation would allow the use of this result as an initial condition for the small x evolution. This should allow numerical evaluation of all NC and NF of any flavor singlets Helicity dependent operator as small x. Thank you for coming.